Okay, welcome everyone. Today our presenters are going to be talking about graph neural networks and LLM on Neo4j, and we'll give the time over to them.
Yeah, thank you very much. And hi everyone, welcome to NOS 2025. And yeah, this session will be about GNNs plus LLMs on Neo4j using PyTorch Geometric. So I'm Brian, I'm a senior software engineer at Neo4j. I work in the graph data science team, and I mainly work on graph machine learning and graph algorithms for the product. And more recently, we're also starting to exploring ways of using those techniques to make GraphRAG better and how graph learning can improve LLM's reasoning power on graphs. So today, presenting with me is Rishi from NVIDIA. I will let Rishi introduce himself in a bit. Before that, let's just briefly go through the agenda. So we'll talk about what is graph neural networks and what is PyTorch Geometric. We'll look at what is GraphRAG and looking at the specific applications of GraphRAG on Neo4j. And after that, we'll look at how graphs can be created from the multiple text documents and how that is supported in PyG with all the latest features that's just released in PyG 2.7. And with that, yeah, I'll hand it over to Rishi to introduce himself and get us started.
Hi, yeah, I'm Rishi Puri. I lead engineering and research efforts on PyTorch Geometric with a specific focus on combining graph and language modeling. And yeah, we have a lot of exciting stuff to talk about today, so I'll just get started. So I want to begin with this slide from a recent talk given by one of the founding fathers of modern AI, Yann LeCun. See the QR code in the corner for the full slide deck that this comes from. The key point of LeCun's slide that I want to highlight is the part mentioning that the probability of being correct is a diverging function with respect to the number of tokens, n. For the equation in LeCun's slides, E represents the error for next token prediction. Even if the error for next token prediction is near zero, the chance of our entire sequence being wrong becomes high very quickly. Because of this, there is an obvious need for some fundamentally new ideas besides brute force scaling of LLMs. This slide has been adopted from a 2023 talk given by the creator of PyG, Matthias Fay. He defines GNNs as models that update node representations by repeatedly transforming and aggregating representations of direct neighbors. The diagrams here explain this quite well, and I will walk through each. The top is the most basic example. We have a single layer of a GNN, which computes the embeddings of any single node. In this case, let's take node 1 as a function of the embeddings of its direct one-hop neighbors. One can think of convolutional neural networks and transformers as subclasses of GNNs, much the way that triangles and quadrilaterals can be thought of as subclasses of polygons. The diagram for the convnet shows how a convnet across pixels is the same as a GNN over a graph of pixels connected to their direct neighbors in the image. For the transformer diagram, you can see that the transformer attention layer is essentially a GNN over a fully connected graph of the tokens. In general, an n-layer GNN learns to predict over n hops of information in the graph, which makes them excellent candidates for enabling multi-hop reasoning in AI systems. This is essential since multi-hop reasoning is a key aspect of human intelligence. An example of my two-hop neighborhood is me, my friends, and all of their friends. Our research finds that GNNs can improve LLM accuracy. We believe this to be possible since GNN embeddings on graph data can provide a semi-orthogonal source of information. LLMs tend to be much larger than GNNs. A transformer layer is essentially a GNN on a fully connected graph between tokens, as we said before. However, the transformer uses parameters to learn the importance of each connection, while GNNs do not need to parameterize how entities are connected, since the graph data provides this information. As a consequence, adding in GNNs has almost no effect on the total number of parameters, as we will see shortly. As an introduction, RAG refers to retrieval-augmented generation. The most basic form of RAG we will refer to as vector RAG. This is where you retrieve the top k most relevant docs based on k and n between the query and the embedding vectors. The diagram in the bottom right corner goes through the basic workflow. This is usually good enough when the answer requires only a single document to be retrieved. GraphRAG is a general term that refers to retrieval methods that retrieve relevant subgraphs for the query. This is generally supposed to shine when the answer requires multiple documents with related entities. Here, we have a diagram of a made-up NVIDIA org chart. The question is, who is the shared coworker between Bob Joe and Ronald Coleman? At first glance, the answer may not be perfectly obvious, even to a human. But thanks to the highlighting of the key nodes and edges, the answer becomes obvious: Arno Schwarzenegger. Using PyG, a GNN+LLM gets the answer right, while the corresponding LLM, fine-tuned the same way, fails to answer correctly, even though both models were fine-tuned on the same general knowledge toy dataset. The pure LLM approach I described is generally similar to most GraphRAG workflows today, such as the one popularized by Microsoft. In school, all students read left to right, just like an LLM. But exceptional students, either mentally or physically, highlight key ideas and form complex relations between them in their brain. I like to think of GNNs and graphs as playing this role for the LLM in a GNN+LLM system. On June 12, 2017, the famous Attention is All You Need paper was added to arXiv. Just 5 days later, Yuri Leskovic's lab published the GraphSage GNN, which is one of the most well-known GNNs, likened to ResNet or AlexNet. Since 2017, the AI industry has poured a majority of its effort into LLMs, establishing a strong foundation to build on. In parallel, a small but strong PyG has begun to grow in academia. There was also a small group of companies capitalizing on the power of GNNs. Examples include Neo4j, Pinterest, Kumo, and Spotify, to name a few. The goal of this GNN+LLM work is to combine nearly a decade of parallel AI research. The goal of this is to add GNNs to LLMs to advance AI systems past the current limitations of LLMs. Now Brian will go into some of the details of how we can apply these systems built into PyG on Neo4j.
Yeah, thank you very much, Rishi. So as Rishi has explained, GraphRAG essentially is incorporating the elements of the graph into the basic vector RAG on documents. So how do we actually do GraphRAG and also use GNNs and LLMs at the same time on Neo4j? Well, the workflow is still pretty much the same as a standard GraphRAG pipeline, right? So assuming you have a graph that's stored in a Neo4j database, and you have a set of questions that you want to get answered. And the answers of those questions lies in the database, which are usually, for example, nodes in the graphs. So you start with the question, and you try to identify the important entities in the questions, for example, by using named entity recognition or taking text embeddings with the question against all the node embeddings. From there, you can identify a few important entities that's been mentioned. Afterwards, starting with those important entities, you can do a cipher retrieval by doing, for example, a few hop expansions around the important nodes. So that will give us a subgraph containing possibly the answers as well as context, and possibly also some redundant information as well, as shown by the gray little subgraph there. So at that point, we might want to prune the graph a little bit because it is still too large to be fed into the LLM for the reasoning step. And for that, we can pick a variety of different optimization algorithms. One such example would be a price collecting Steiner tree, where we assign prices on nodes and costs on the edges. Afterwards, we will obtain a much smaller subgraph, as shown by the little blue subgraph in the bottom, and that becomes the context containing the answers. Okay, and we feed the graph with the properties to the GNN, and we also textualize the graph and send it to the LLM. And the GNN and LLM together can help us obtain the final answer. So let's look a little bit more into the details of each component. Yeah, next slide. Yeah, so the first step, as we said, we need to identify some important entities. So assuming that the entities have been identified, well, we have the database, we need to create a vector index, right? So standard way of doing this is db.index.vector, and you can query the nodes using the index, specifying the number of nodes you want to find, and also the query embedding. Afterwards, we obtain grounded entities that's returned from the database. And from there, you can do a variety of multi-hop expansions, possibly with constraints on the types and filtering on the properties to give us the subgraph. Afterwards, as we said, we might want to apply some optimization algorithms to trim down the graph a little bit. So in this case, we can, for example, run the node price collecting standard tree, which is a two approximation algorithm. So what it means is that this approximation algorithm is at most 2 times more costly than the best possible solution that you could find using the combinatorial ways, which is extremely slow. So it is a great implementation of an optimization algorithm, which offers us efficiency as well as a guarantee of the quality, right? You can also apply a variation of this algorithm with prices on edges, which loosens the constraints a little bit. And we also know for sure what is the complexity of that, and therefore we know roughly how long it will run. So instead, we obtain a subgraph. We can feed that into the GNN+LLM. And the LLM of choice, for example, could be some open source models such as Llama 3, Quen, Gemma, etc. And GNNs could be, for example, GraphSage, Graph Attention Networks. And typically for models of this size, all you need is about 4 40 gig GPUs, and you're able to do an inference as well as fine tuning on that. So again, this is basically the framework and the pipelines that we can use. The details of the cipher pattern matching as well as the parameters that you would pick for a price collecting standard tree would vary depending on the different questions and data sets that you have. So now let's look at an even more concrete example on a specific biomedical data set. Next slide. Yeah, so here's an example of the Stark Prime data set produced by Stanford. It is a biomedical data set containing 129K nodes and 8 million relationships with a variety of node types and relationship types. Therefore, it's a quite challenging real-world large data set. So the typical questions you have there will represent those of a patient, of a doctor, of a medical scientist. For example, here is one such question, right? We're interested to know particular drugs which target some specific enzyme and that are used to treat a specific disease. Okay, and the answer is one of the drugs that is provided in the database. So how can we do that? Well, what we do is apply the GraphRAG pipeline with GNN+LLM that we've just described. So we start with identifying the relevant nodes. In this case, it's the specific enzyme and the specific disease. And we decided to use a 5-hop expansion around the two entities, connecting the two entities together, as you see with this example cipher query. Okay, and in the expansion, we also add constraints on the node types. For example, as you can see, for the node X2, we are interested in being disease because that is what is being expressed in the question. With this, we'll be able to obtain a subgraph. So the next part. Yeah, so we obtain a subgraph, and if we run price collecting standard tree on that, we're able to shrink the graph down significantly. So this is an example such a small subgraph which we might be able to obtain using PCST. What we want to do is to feed the subgraph as well as the textualized graph into a GNN and LLM. And how do we do that? We take the graph and the edge list and also numerical properties on the graph, and we simply feed it into a GNN to generate embeddings, and we pass it through a linear layer to project that into the same embedding space as a token space of LLMs. For the textualized part, we simply take the graph and describe in text, right? So we describe the 5 nodes with the textual properties on it, and also the edges. And we feed that into the LLM, text embedders as well, and create a list of text tokens. And together with that, we pass the concatenated tokens to the transformer self-tension layers, and the GNN+LLM is able to together generate the answer token, which in this case is ivermectin. So let's look at some benchmark results on the next slide. Yeah, so as can be seen here, what we've shown is a typical workflow by the paper GRetriever, and we are able to obtain a hits at 1 score, which doubles the previously best result, right? So we are able to get 32% as compared to 15%, which is the best result previously, as shown by the leaderboard for Stark Prime. A small modification of GRetriever by concatenating the subgraph context to the output of GRetriever will even further improve the results, especially for hits at 5, recall at 20, and mean reciprocal recall because that adds more answer nodes to the final answers. And therefore, we're able to obtain a significantly higher metrics for every metric across the board. And there's a little diagram there which also shows the time taken for each step, right? The three main steps are cipher, price collecting standard tree, and GNN plus LLM. And all three steps are extremely efficient. Furthermore, we did some further improvements with additional fine-tuning as well as a constraint decoding for the cipher step to make sure the cipher is guaranteed to be executable. And we're able to show that even with a fine-tuning on the 10% of the training dataset, we're able to obtain an even higher benchmark results, which is significantly better than all the results that we know. So all the benchmarks shown here, as well as the code being produced, are in the GitHub link. The details are shared in the technical blog. And for the GraphRAG technique, we will also link the archive paper here. So I've just talked about how we can use GraphRAG with GNN plus LLM on Neo4j. But that assumes that there needs to be a graph in Neo4j, right? And in many cases, there isn't such a graph, and our information is being represented as text or in multiple documents. So Rishi will then show us how we can convert text into graph using features added in PyG 2.7.
Yeah, thank you so much for that great talk. Yeah, so one of the key issues, as you mentioned, is that most RAG datasets only have unstructured text context. As such, there's often an additional task where we must convert this unstructured text into a knowledge graph format. Our existing PyG framework uses the simple KG format of triples, basically parentheses, entity, comma, relation, comma, entity. As mentioned before, LLMs are specialized for handling unstructured text, so they are the ideal model for this task that we've found so far. As our solution to the problem, we have created the text-to-KG class in PyG 2.7. This system is not really rocket science. It just consists of a combination of frontier model prompt engineering and some Python filtering on top of it. If you look at the top image, that snippet is the current system prompt for this class, and the snippet on the bottom shows how easy it is to use. You just basically for loop over a list of strings and you pass it in and it'll create your knowledge graph. So in general, we should expect that combining vector and GraphRAG is always at least as good or likely better than either alone. And this is because GNNs help the LLM decoder to understand graphs, producing better accuracy. This diagram covers the fully combined workflow, which they have basically mirrored in Neo4j as well, with additional improvements such as GraphRAG, which is a really powerful technique. As you can see, this is the same diagram or similar diagram, but we've added in the, basically you can add in whatever document retrieval technique you want. Basic vector RAG works. There's a whole space of research into that field as well to do more advanced techniques. We find this to be the optimal system for now, and we'll continue to refine it as we explore further. Remember that in general, we only expect accuracy boosts for adding graphs and GNNs when the question requires multiple entities to answer them, or basically multi-hop. Basic vector RAG is plenty good at handling questions where basically a single fact can answer the question. So that's definitely something to keep in mind before diving in and investing in this. But in general, most things that can't be solved today with AI are multi-hop. So this is kind of the final frontier that we need to start working towards, and I think this is a big step in that direction. So this system is seeing adoption throughout NVIDIA and across many Fortune 500 companies. And yeah, you can see either the code repo they have if you want to interact with Neo4j, or if you want to just build your own custom solutions. There's the examples in PyG, which basically is they're one and the same ultimately algorithmically. In this experiment, we measure the accuracy of a Llama 3 8B generator by using a much smarter 253B reasoning model as the LLM judge. The question answer pairs for this test were generated synthetically to use multiple chunks of text for each question. We consider the speed of light to be when we feed the generator with the exact context that was used to generate the question answer pairs. You can think of this as basically cheating on a test, right? This is what we would consider to be perfect retrieval. Notice how we are only 1.1% accuracy away from this speed of light. We also perform much better than basic RAG solutions. Keep in mind that we did not do any hyperparameter tuning to achieve these results. That is, we use the same set of default hyperparameters across the board. So, this example, along with what Neo4j showed on Stark Prime, starting to paint a pretty convincing picture that this does really help in the RAG space, and it's really important for hard RAG questions such as multi-hop questions, which Stark Prime is. This synthetic data also covers. So generally, yeah, if you have hard questions, I highly recommend looking into what Neo4j has done or just what's in PyG in general. This slide covers a demo made by our PM, Santosh Bhavani, who was able to upload our PyG code to Cursor and have Cursor completely vibe code a graphical interface on top, showing how easy our framework is to build upon. This is now released as an NVIDIA product, but I will skip the video for now for time's sake. If there's time at the end, we can circle back to it. But see the link there for details. As a final note, today there are two kinds of GNNs. The traditional kind are the message passing GNNs. Then there are graph transformers, which are newer. See the QR code for a webinar on the topic I gave with Stanford and Kumo AI. I'm working with the community to get more graph transformers added to PyG. My general goal for this would be to see how these affect the accuracy of the previously discussed GNN+LLM systems. In general, most AI practitioners will agree that data is the most important part of a deep learning pipeline, as it is your source of information. For example, even the best model from 100 years in the future can't learn anything if your data is fully randomly labeled. Graph models, which began as GNNs and are growing into graph transformers, will continue to evolve. But the key takeaway should be that structured data can help improve the capabilities of AI, which today learn mostly on unstructured data. Neo4j, as one of the best solutions out there for structured data, is a key part of this pipeline. This work is built and optimized for the NVIDIA PyG container, and we will continue to collaborate with Neo4j on further improving this. Just stay tuned to LinkedIn for any further updates. As a final note, I want to acknowledge all of the contributors on this effort, especially just in general, the entire PyG community. The PyG community is ever growing and contributions are always welcome. Yeah, thank you.
Yeah, thank you very much, Rishi. I think it's worth pointing out there on the final slides, among all the contributors, there are people that's working in both NVIDIA PyG team as well as Neo4j, who's contributed to all the content that we've shared. And which is a truly cross-organization collaboration in this case. Okay, I think we have a few minutes left, and there are some questions that I see in the chat. So perhaps we can go through some of those questions. Let me have a look. Okay.
I mean, I saw one of them based on this basic RAG did better than basic GraphRAG. That's the takeaway. Basically, if you're just feeding, like I can go back to a slide that might help explain this.
If you can share again, it would be great. Yeah.
Shoot. Give me a second. How did I share screen? I'm sorry. I figured it out. Sorry. So if you look at this format, this is what your LLM is seeing, right? And it's just reading this left to right. So generally, LLMs are not designed to understand this kind of formatting, right? When you read English, left to right has an implied ordering. There's a meaning implied by that. Whereas when you read a graph, the left to right ordering is kind of meaningless, right? You could shuffle these nodes and edges. It would be the exact same graph, right? And so in general, if you're not giving the LLM an ability to read the graph the way a graph is meant to be read, it can almost just act as noise. In general, like vector RAG is not a terrible solution. It does work pretty well. And if you're going to add the complexity of graphs, you have to give a model that's designed to understand graphs. And so, yeah, Neo4j and GNNs are a key part of that. But yeah, if you just kind of feed the text of a graph to an LLM, it does worse than reading the documents from which that text, I mean, like the graph was derived from the documents, right? And so you're basically just imposing some noisy filters on top of it. And if the LLM can't understand that reformatted version of the documents, it makes sense that it's going to do worse. So generally, if you have some easy stuff to do, use VectorRAG. But the whole pitch of this is that all that easy stuff is already solved out of the box by so many solutions out there that if you have real hard tasks, Neo4j and PyG is the way to go, I would say.
Yeah, thank you, Rishi. I saw a few more questions, which maybe one of them I can answer. So is there similar activity research for RDF data? I would say not really. So for us, we're more interested in the labeled property graphs and all such graphs in the graph databases like Neo4j. But to be honest, all the techniques here equally applies well to RDF data or any other representations of graph data, right? Because the methods are agnostic to how your data is actually represented inside the databases, whether it's RDF or LPG. Now, I saw another pair of questions that's quite similar. So one is, what exactly is the GNN doing here? Why can't I pass the text of the subgraph to the LLM? And the other question is, GNN part added only as an embedding that is additionally passed to the LLM, or does it do something else? I think they are great questions, which are quite similar. And Rishi, could you go to slide 10?
Yeah.
So basically what the GNN does is that you take the graph, the adjacency list, and the node embeddings, and you feed it to the GNN, which will generate a node embeddings based on a neighborhood structure, right? And that's what the LLM is not able to do. The LLM part takes the textualized graph. Most importantly, you need to include, for example, textual descriptions such as names, descriptions of the medicines and drugs, and feed it to the LLM for that. And this basically also echoes with what Rishi was saying at the start, that they're offering semi-orthogonal information. So the GNN is much more powerful and actually provably powerful in capturing different topologies directly, whereas the LLMs are largely just doing the embeddings on text tokens. And we're not sure whether it's able to capture such topologies at all. And with all those embeddings being concatenated, you feed it to the later layers of the LLM. Or perhaps more precisely, the later layers of transformers, which are the self-attention layers. And that way it can generate the final answer using the semi-orthogonal informations produced by tokens from the GNNs and the tokens from the LLMs. Okay. Okay, another new question. Does PyG work on data inside Neo4j directly or not? Or export from Neo4j first? That's a great question. So in the example repository, which we have linked, we have examples of how you can use PyG on Neo4j in a more tightly coupled way, where you don't have to kind of export everything upfront. We're actually doing more work right now to have even better integration between PyG and Neo4j. For example, extending the PyG feature store and graph store to natively supporting direct cipher retrievals. For example, when you train GNNs or when you do an inference with GNNs. And there's also a new RAG query loader in PyG 2.7 that's just released a few weeks ago. And we're also extending that to make, for example, you could call a Neo4j RAG query loader, which would also couple that with Neo4j better. And I'll also send the link in the chat. Okay, I think we're pretty much time. And yeah, thank you very much again, Rishi. And thanks everyone for coming. Enjoy the rest of notes. Thank you. Bye.